In the distant reaches of the solar system, far beyond the warmth of the sun, lies a realm of ice and shadow. Saturn, the ringed giant, turns slowly in the twilight, encircled by a retinue of moons. Among them, one shines brighter than all the rest. A moon so small it could fit inside the continental United States, yet so remarkable that it has become one of the most promising places in the universe to search for life. Its name is Enceladus, a world of contradictions. Frozen on the outside, yet warm within. Quiet and serene from a distance, yet erupting with colossal geysers that reach hundreds of kilometers into space. When NASA's Cassini spacecraft first flew past it in 2005, scientists expected to find a cold, dead rock. Instead, Cassini revealed something astonishing: jets of water vapor and ice blasting out from fissures at the moon's south pole. Fountains so powerful they form a glowing halo around the moon and even feed Saturn's E-ring. Those plumes told a story of heat, motion, and perhaps life. For where there is liquid water, energy, and chemistry, there may be biology. And so began humanity's fascination with this tiny world, an obsession to know what lies beneath its shining crust. Beneath kilometers of ice, radar data and gravitational mapping suggest the presence of a global ocean, vast, dark, and liquid. An entire world of water beneath ice, kept warm by tidal forces and possibly alive with chemical reactions that mirror those that birthed life on Earth. Beneath the surface of Enceladus lies one of the most extraordinary environments in the solar system. Cassini's instruments, designed to study moons and rings, stumbled upon something far more profound: evidence that Enceladus's ocean is not just water, but a dynamic, chemically active sea. When Cassini flew through the plumes, it collected microscopic ice grains and vapor. Inside them were traces of salt, methane, hydrogen, and complex organic molecules, the same molecular ingredients that form the foundation of life on Earth. Even more astonishing, Cassini detected signs of hydrothermal activity, heat from the moon's core interacting with seawater, producing molecular hydrogen, a fuel source for microbes here on Earth. On our own planet, deep beneath the ocean, sunlight never reaches the seafloor. Yet around hydrothermal vents, life thrives. Entire ecosystems powered not by light, but by chemistry. Worms, shrimp, bacteria, all feeding on hydrogen and methane in total darkness. Now imagine that, beneath the ice of Enceladus, similar vents are erupting on a rocky ocean floor. Imagine the chemical gradients, the warm currents, the potential for alien life. Not intelligent beings, but microbial pioneers, living chemistry sustained by heat and minerals. Recent reanalysis of Cassini data revealed phosphorus, a crucial ingredient for DNA, RNA, and cell membranes. This discovery was stunning. It meant that Enceladus has all 6 essential ingredients for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The ocean beneath Enceladus's crust may be a complete ecosystem, isolated for billions of years. If life began there, even simple, microscopic life, it could represent a second Genesis, proof that life arises wherever conditions allow. After Cassini ended its mission in 2017, burning heroically in Saturn's atmosphere, one question lingered: when will we return to Enceladus? Across the world, mission planners, engineers, and astrobiologists began designing the next generation of explorers. Concepts emerged: Orbalander, Enceladus Life Finder, Enceladus Icy Worlds Explorer, each with a single goal: to determine whether the ocean beneath the ice is alive. These missions envision spacecraft capable of flying through Enceladus's plumes, collecting material directly from space, and analyzing it for signs of biological activity, amino acids, lipids, isotopic ratios, and complex organics. Some concepts even include landers to touch down on the icy plains, where fresh snow from the plumes settles like cosmic frost. Picture it, a gleaming spacecraft approaching Saturn, the giant planet's rings stretching across the horizon. As it nears Enceladus, the moon's icy surface reflects sunlight like a mirror. Plumes rise from its south pole, jets of potential life, and the spacecraft dives through them. Its instruments open like cupped hands, catching dust grains and vapor. Inside its onboard laboratory, the molecules are separated, measured, compared. The data transmitted back across the solar system, a stream of numbers that may one day answer humanity's oldest question: are we alone? Each pass through the plume deepens the mystery. Each sample hints at complexity. And as the spacecraft orbits again and again, scientists on Earth begin to piece together the story of Enceladus, a world of fire and ice, of chemistry and motion, of secrets locked beneath frozen silence. Exploring Enceladus will not be easy. It lies more than 1 billion kilometers from Earth, a distance that light itself takes over an hour to cross. Communication delays mean every maneuver must be planned meticulously. Every system must be autonomous. The spacecraft will endure extreme cold, radiation belts, and long years of silence. Its instruments must survive the harsh environment of Saturn's system and still function with absolute precision. But the greatest challenge is not distance, it is interpretation. Even if we detect complex organic molecules, how do we know they are biological? Life leaves subtle signatures, patterns of isotopes, asymmetry in molecules, organization in chaos. But nature can mimic biology in surprising ways. To be certain, we must look for multiple clues, a combination of chemistry, structure, and context that together whisper, life was here. And then comes the moral question. If we find evidence of life, should we go further? Should we send landers to drill through the ice, to touch the alien ocean? Planetary protection laws demand caution. Contamination could ruin pristine ecosystems or destroy fragile biosignatures. So our first missions will be careful, eyes, ears, and hands extended gently into the void. But one day, when technology allows, humanity may send a submersible probe descending through the ice into the darkness below. Imagine it, lights piercing black water, drifting past mineral chimneys, bubbles rising from the seafloor, and perhaps the flicker of movement. A discovery like that would change everything. The definition of habitable world would expand beyond sunlight and atmosphere to include ice worlds, ocean moons, and hidden biospheres. It would prove that life is not the exception, it is the rule. When you look at Saturn through a telescope, Enceladus is barely visible, a point of light in a sea of darkness. Yet that tiny world may hold the answer to one of humanity's greatest questions. What does it mean if life exists elsewhere? It means that we are not alone in the universe, not special, not unique, but part of a greater cosmic story. Life, it seems, is not rare stardust. It is a natural consequence of chemistry and time. And what if Enceladus is lifeless? What then? Then it teaches us humility. It reminds us how fragile life is, how miraculous our own planet's warmth and complexity truly are. Either way, Enceladus will change us. The mission to Enceladus is a bridge between science and wonder, a message that even in the coldest corners of the cosmos, there may be warmth, movement, and purpose. It's a reminder that life finds a way, perhaps not only here, but everywhere water and energy meet. Someday, when our spacecraft touches the icy surface of Enceladus, when instruments dip into its hidden sea, when data confirms that living chemistry stirs beneath its crust, that will be the moment we understand the universe anew. And maybe, just maybe, we'll realize that the search for life beyond Earth was really the search for understanding ourselves, fragile, curious, and eternally reaching for the unknown.